Uh, Good afternoon, ma'am. Welcome all.
गुड आफ्टरनून.
मैम अभी वो YouTube लाइव में है हमारा
Okay,
सेशन.
okay. It has started streaming.
Yes, ma'am. It is already streaming. I'm sharing the link here.
Okay, thank you.
Same
Good
link.
afternoon, all the participants. So today we are going to discuss a very important type of neural network known as convolutional neural network. I told you on the first day that there are several types of neural network, and they have proven to be very useful in different applications, right? So let us begin with neural network for image data. Suppose your image input vector is an image, right? Your input vector is an image, suppose. And task is to classify if the image contains a bird or not. By just looking at this picture, you will immediately tell that, well, there is a bird. But this picture is a little tricky picture for an automatic system because the bird's color is quite close to that of a flower. Now, suppose the question is to detect a bird in an image, and each image is of size 256 cross 256. Okay.
I'm
So
sorry to.
size of the image.
Yeah, ma'am.
Yeah. Yeah.
Yeah. Can you wait for 2 minutes?
Okay. Okay.
Somebody actually messaging that they're facing some problem in joining.
All right. All right. I'll start again.
Just 2 minutes, please.
Fine. Fine. No problem. First of all, you have to join on WebEx for your attendance. YouTube is for a later reference. So please don't get confused. YouTube is if you wish to refer the lecture again, then you have to join. So there's nothing like where to join, okay? Please tell me when I have to start, I'll start. So it is 3:05. I think we can start, and hope people will join soon.
Yes, ma'am. Now they have almost everyone is joined.
Yes.
Yes, ma'am.
Okay. Okay. Thank you. So, my dear participants, we were talking about convolutional neural networks, an important neural network type for, especially for image data. So, let us consider this classification problem. And suppose the input image is of size 256 cross 256, and the problem is a binary classification problem, whether the image contains a bird or not. Now, because the image is of size 256 cross 256, if you consider an ordinary like multi-layer perceptron, what will be the size of the input layer? That will be 256 cross 256, that is 66,536. That will be the dimension of the input layer. That means each sample is of this dimension, has 66,536 features. And if the first hidden layer contains, say, 1024 units, how many weight parameters will be involved? Can you imagine? So you can see such a big number that is appearing here. And these many weight parameters will be there only in the very first hidden layer, right? So image data, which is a high dimensional data, if we consider these fully connected network, it becomes a huge parameter training problem, right? So let us look at the image data characteristics. One is very clear, that is, it is high dimension. Second, it has certain redundancies, if you see, or you can say that there are some repetitions. So this is an image block where I've taken pixel values of from one of the channels, RGB channels. Wait for a while, just wait for a couple of minutes. Sorry. So if you look at this, you can see that there are so many redundancies, right? And the third important aspect is patterns. In image data, you will find patterns which will be appearing or which will be repeating in the entire image. So if I look at the convolutional neural network, uh, if I look at the traditional neural network, that is multi-layer perceptron, the question is, do we actually need these edges in this fully connected layers? Are they going to help us gain something new from the image data? And can some of the weights be shared? Is it possible that some of the neurons are sharing the weights? So, because it may happen that two neurons which are independently processing the information might be looking for some important feature of the image. And that feature might be the same feature as well, right? So with this, let us consider this problem of image understanding. First of all, these patterns that we have to learn from the images can be very small compared to the image size. For example, eye detector in an image. So here you have an eye detector, which is, so eye detector requires very small portion, very small image block, right? So a small pattern detector can be used in place of the entire fully connected hidden layer. You can use only a small portion, a small eye detector pattern, detector. Now, if I look at this pattern, the same pattern can be at different positions in image. For example, here in this case, eyes are appearing 4 times. So don't you think that the same pattern detector can move around the image to determine, to find out the pattern at different places, right? So with this, keeping this idea in mind, convolutional neural networks are defined. They use parameter sharing. Parameter sharing means the same pattern detector is sliding over the entire image and trying to detect a pattern, right? So basically, when I'm saying that same pattern detector, that means the same number of parameters are used to detect a pattern. So this small pattern detectors called filters are used to convolve over the entire image, right? And these filters are learned through neural network training in the same way as the fully connected network. So in the fully connected network, yesterday and day before, you saw that there's a forward propagation of the input, and then the neural network tries to extract features, make its own decision or makes prediction, and that prediction can be very close to the actual value, or the prediction can be different than the expected outcome, right? In both the cases, you have error, and that error is back propagated by taking the gradient of the error with respect to uh, considering this error as a function of weights and bias parameters. So in a similar way, convolutional neural networks are also trained. The only difference that we have here is that they're using patterns, or they're using filters, sorry, for detecting patterns. So just can you hear me? Can you hear me? Hello, can you hear me? Hello, am I audible?
Yes, ma'am, we can hear you.
All right, because there was some disconnection. So I'm sharing again. All right. I'm extremely sorry for the inconvenience caused. So just like a hidden layer in a fully connected network, my dear friends, convolution layers are introduced in CNN. Okay. So what kind of convolution layers? Let us understand what exactly is convolutional operation. In a couple of minutes, I will tell you what exactly is done in a convolutional layer. Now, to handle large size data, because the images are generally of large size, pooling layers are also introduced in a convolutional neural network. All right. And there are certain layers which are known as batch normalization layers or normalization layers. They are used in CNN architectures to accelerate the training process. In this layer, what happens that we consider a batch of input. They are on those batch of input, convolution is applied, and then after application of convolution or after application of even sometimes pooling, then you look at the average, that is the mean of the input and also the standard deviation. So we shift and rescale the things so that mean and standard deviation Mean is at 0 and standard deviation doesn't go beyond 1. Right. So let us try to understand what exactly is convolution operation. So think of an image. Here, this is an image which I have plotted here. Suppose this is an image and this is a small block of the image. All right. Very small block of the image. It can be 3 cross 3, 5 cross 5. Now, what I do is that I use a filter. What is a filter? It is nothing but a block of the same size that is plotted here, right? So suppose it is a 3 cross 3 block or a 5 cross 5 block. This is a filter that I'm choosing here. What I'm doing is that I'm convolving this filter values, that these will be real values, with the image pixel intensity value. So convolution with an image block outputs a real number. If I take a 3 cross 3 filter and if I have a 3 cross 3 image block here, they will be convolving with each other and we get a single real value. But when we slide this filter over the entire image, we will get an array of real numbers. That is the output of the convolution operation. So if I have this image, I have slided this filter over the entire image, then I get an output which is shown here, right? So from this image, you get an output like this, okay? So you get the output of a convolution layer, and for each filter, you get one output array like this. There can be many filters, many pattern detectors, and for each filter, you get one output array like this. So let us take an example to understand how exactly the convolution operation is performed. Right, so suppose this is the filter. This is the filter size. And suppose this is the image size. So suppose the image is, the image is n cross n. And suppose the filter is of size f cross f. Here f is equal to 3, I have taken. And n is equal to 6, we have taken as an example. Okay. So here I have chosen randomly the values of filter. Just like you choose weights randomly in the hidden layers. So here randomly I have selected some values of this filter. An image is definitely an input which will be fixed. There's no randomness in that. It is a sample that I am using, input sample, right? Now let us see what we are going to do. I will place this f cross f filter or 3 cross 3 filter in this case on this image block containing these 9 inputs 517, 725, 535. When I put them, when this filter overlaps with that, what happens? We see that the numbers like this one coincides with 5, 0 coincides with 1, -1 coincides with 7, and so on and so forth. To understand how exactly convolution is performed here, I convert the image block and filter to single column vectors and calculate their dot product, right? So suppose x is this. So what is x? I take 517, 725, 535. So I make this one full one full single column vector. So it's a 9-dimensional vector which I have taken. And this, let me call this as W, this filter as W, and this input block as X. Okay. Then W transpose X. Why I am doing this? Because you have understood the neural network in this form, and therefore I am converting this 3 cross 3 image block to a 9 cross 1 vector, and similarly W, the filter to be a 9 cross 1 vector. So W transpose X becomes 5 cross 1. So now I'm doing W transpose X, that is taking the dot product. I hope you understand why we take transpose here. Somebody was asking the other day on the first day that why do we take transpose? You cannot multiply W and X. You have to take the transpose so that the dimensions match for matrix multiplication. All right, so finally you get 2. I can see so many questions are being floated and comments are being made there. Please give me some time to explain the entire process, and then I'll answer your questions after some time. Now, once this is done, I get one value. That value is 2 here. This value is 2, as you can see, right? Now, I slide this. So I slide the filter with a stride S is equal to 1. By stride, I mean I'm shifting by 1 pixel at a time, right? So I'm shifting this filter on the image by 1 pixel, okay? And then I do the same process. That is, I take the dot product, I get another number. So what will be the output size after the convolution, entire convolution is performed? Can you tell me? Please write your answer on the chat box. Please write your answer in the chat box. If suppose I take all the strides and then go down 1 pixel at a time, what will be the size of the output? See, I get when I'm plotting, I get one output from this, second output from this, the third output from this, and the fourth output from this. So I get 4 outputs, right? I will be getting 4 outputs if I slide it horizontally. Now I will be sliding it vertically as well. So first output from this is the first output. The second output from this. Now, similarly, you will be sliding it horizontally again. So this is the third output, and this is the fourth output, this is the fifth output. In fact, in this row, these 4 outputs will be given. So 4 outputs. Now I slide it further down. I take 4 outputs again. So you will be getting 4 outputs. And then you will further be sliding down and you'll be getting 4 outputs. Do you agree with me? That the output will be a 4 cross 4 array. It will be a 4 cross 4 array. So many people are writing here. I hope you have understood this. So this is a convolution operation performed in a convolution layer. So convolution layer, you can see that if suppose this is the image on which you are performing a convolution operation, so you can see that the same number, same W values are used when I shift the filter, then same W values are used. So whatever is shared by 3 is also shared, for example, in the next time by 4 or by 10. So we may think of convolution layer as a hidden layer in which various weight parameters are same, or there is a concept of parameter sharing. Okay. So this is how you can see that weight parameters turn out to be the same. So convolution, I hope you have understood how a convolution operation is performed on an image. And if suppose the image is RGB image, then it will have 3 channels, isn't it? In case of an image with RGB channels, we perform convolution operation on each channel separately. Make 3 copies of this filter. Suppose you have a filter which was given here. This is the filter. Now what I will do, I will use the same filter 3 times. One for R channel, one for G channel, and one for B channel, right? So in case of an image with RGB channels, perform convolution operation on each channel, make 3 copies of the filter and apply convolution operation. Now you will get 3 values, one for each channel. Like suppose an image pixel X is given as RGB, or image block is suppose X is a block and X is having R channel, G channel, B channel, right? Red, green and blue. Add all 3 values of the filter mapping to get a single output. So what I do is here is that I'm calculating W transpose R exactly in the same way as I did before. Similarly, W transpose T and W transpose B, right? For R channel, for G channel and B channel. This is how I am doing it. So this channel, this filter is applied on this image block. Is that okay? So now for convolution on RGB image also, exactly same thing is done, except that all the channel outputs are combined. They are added to give you one value. Now, so you have this image, right? 6x6 image. Suppose you have got H filters. I want to apply H filters. You will ask me why? Because there can be many patterns in the image. One filter will learn to detect one pattern only. I want to detect several patterns simultaneously, and therefore I will be applying different filters and I will be training. I mean, the network will be training different filters to detect different patterns. So suppose there are H filters. So what will be the size of the output? I told you it is 6x6 image with a stride of 1, 3x3 filter. You will be getting the size of the output as 4x4x H. So output will contain H channels. These channels are known as feature maps for each filter. So each filter produces one feature map, right? So let us consider this input image of size n cross n. And suppose there are H filters of size f cross f. Somebody was asking, is it necessary to take 3x3? I hope I have answered your question. Not necessarily. H filters of size f cross f, and they will produce H feature maps irrespective of the depth of the image. Please mind you, I'm saying irrespective of the depth of the image. The image can be an RGB image. The image can be a grayscale image. The image can be a satellite multi-sensor image. So depending on, or it can be RGB alpha, where alpha is a transparency factor in an image. It can be 4-channel image. Whatever is the input size, the output depth or output volume will be determined by the number of filters that you choose in your convolution layer. So convolutional layer contains, suppose, H filters of size f cross f, then H feature maps will be produced, and each feature map applies its own bias. Just like each neuron applies its own bias, so each filter applies its own bias. So the output will become what? Z, suppose Z is the output, Z will be equal to W transpose X plus B, where X is the input image. All right. So that is feature map. What is activation map? Now, sometimes people do interchangeably use the word feature maps in activation maps in the same way. I mean, they are using activation maps are also sometimes known as feature maps. But for us, we will call activation maps to be a map which is obtained by applying activation function on each feature map. So an activation function is applied on all the entries of each feature map to get the activation maps. The output, that means the activation map, consists of entries of the type A, which is equal to f of z, which is equal to f of w transpose x plus b. All right. So if I look at this example where suppose you have 6 5x5 filters, you will be getting 6 separate activation maps because we have 6 filters, irrespective of the input dimension, which was 3 in the depth. I'm talking of depth dimension. It was having 3 channels. The output depends on the number of filters that you use. I'm repeating it because several times we have found that people get confused with the input and output volume dimensions. All right. So activation map, this is one particular example of an activation map for plant disease detection problem that Purnima, my student, is working on. So we work on this plant disease detection, localization, and many related problems for smart agriculture solutions. So you can see that if I wish to plot the activation map for coming out of an convolution layer, so it was the second convolution layer, and the activation maps look like this. If I go deeper, say 7th convolution layer, or the 10th convolution layer, or the 13th convolution layer, you can see that the level of abstraction increases. So at the higher level, at the deeper level, more abstract or higher abstraction level features are detected. At the lower, that is at the shallow level, definitely the features are detected. The what should I say? The convolution layer detects some features of the image input, but those features are of low level. And then comes mid-level features and then the high-level features. Those high-level features are of higher abstraction level. Similarly, if I take a case of wireless capsule endoscopy images, in which another student, Samir Jain, is working. So you can see that the feature maps that are coming out, or the activation maps which are coming out, are somewhat of this type, right? Well, I will answer your questions only after some time. I can see that so many questions are being repeated and are being asked, but please have some patience. We will definitely answer your questions. Now, if I look at the filters and the activation maps, you can see that this is a example of a car. You have a car bonnet and the car headlight. Now, from this car headlight, you have suppose 5x5, 32 filters. Now, these 32 filters give rise to here these 32 activation maps. Because we have 32 filters, you'll be getting 32 activation maps, right? When you see these activation maps, you must have seen that there are certain maps which are quite similar, like this one and this one. This one is quite close to, say, this one. So there are some similarities, right? So number of filters in a single convolution layer are chosen by the user of the CNN. Depends on the application and the data input type. You must be thinking how many filters should we choose? So that depends on application If the data is having a high entropy, it's having variety, then in that case, you should choose large number of filters. So typically, a sizable numbers of filters are chosen to extract the maximum number of features so that we don't miss out any features of the image, right? Or any patterns which exist in the image must be detected. So I told you that some filters detect almost same patterns. So the number of filters can be extra and can lead to redundant information as well, as you saw. But if I take a small number of filters, what happens that sometimes we lose the to capture the image characteristics. And therefore, it is always better to choose a larger number of filters than stick to a small number of filters. Where if you choose large number of filters, the number of parameters, weight parameters will be high. But if you choose a very small number of filters, you may be missing many informations which are important for a specific class of problems. So a small number of filters are generally not chosen in spite. Sometimes, your image appear to be very simple. Even then we choose large number of filters. So it is better to use a large number of filters to avoid any kind of information loss. All right. Now we come to output volumes. So what is an output volume? I told you that the input volume is the input image. But after the first convolution layer, the output that we will have its height, width, and depth as well, depending on the number of filters. So that is why we call it output volume. So operation with filters produces an output volume, and filter values are initially chosen randomly, as I told you. Gradually, values of the filter are updated in each iteration. How they are updated? I hope you remember. The values are updated like any W value is updated like this. W is equal to old W minus learning rate del J by del W, right? And similarly, bias is updated like B minus alpha del B by del W. So they are gradually updated. So what is this del J by del W? It is basically the partial derivative of the cost or the error function on a batch of input images. And then we take the average error, we take the gradient of the average error, and then we back propagate that gradient information so that each W can be adjusted. So suppose the image is 256 cross 256 cross 3, and there are 8 filters, each of size 5 cross 5. What will be the output volume? Please tell. I expect an answer from you all. What will be the output volume? Please calculate. Five cross 5. Filter is of size 5 cross 5. And input is 256 cross 256 cross 3. Definitely, this 3 is not going to play any role. I hope you agree with that, because your input spatial dimension is 256 cross 256. There are 8 filters. So the depth of the output volume is certainly going to be 8, right? There are 5 cross 5 filters. You will be, suppose you are taking a stride of 1, you will be shifting up to what level, right? You can shift up to what level? When 256, the last, like 256, like you start from say 1, 2, 3, 4, 5, you go up to 256, 255, 254, 253, 252, right? So you have a 5 cross, so 252 to 256. That will be the last position of the filter. So I'm asking you to do a little bit of mathematics to explain what will happen, to understand what will happen. So each filter 5 cross 5 will be converted to a 5 cross 5 cross 3 filter volume. Why? Because your image is of size 256 cross 256 cross 3. So I will transform this 5 cross 5 by making 3 copies of 5 cross 5 to 5 cross 5 cross 3. Then it will convolve with each block of size 5 cross 5 cross 3 in the image to just one, to give you just one output. I can see so many answers coming out, and Neha, Bhagwani, Aditya, so many of you have very correctly given that the whole convolution process with one filter will give a layer output of size 252 cross 252, and because it is one filter, and so there are 8 filters, so you will be having 256 cross 250, sorry, 252 cross 252 cross 8, right? So I hope you have understood to some extent. Now let us see the formula. So you have n cross n is the size of the image. You have f cross f size filter. The output size will be n minus f plus 1. That's all. N minus f plus 1. And if there is a stride more than 1, like if suppose the pixel shifting is by say 2, then stride will be 2. In that case, it will be divided by strides because it is number of times it can slide will be just the half. So suppose n is equal to 6 and f is equal to 3. What will happen if the stride is 3? What will be the size of the output? Yes, if n is 6 and f is 3. If the stride is 3, what will be the size of the output? Somebody is writing 7. No, it's not 7. It's a 2 cross 2. Very simple. It's a common sense, right? And n is equal to 10 and f is equal to 3. And stride is again 3. What will be the output volume? Now 10 is not divisible by 3. You will be having still 3 cross 3 because the filter cannot move further, right? Okay. Now, let us look at another important thing which is known as zero padding. Now what happens that the corner image pixels, they are not very much well represented as the inner pixels of the image in a convolution operation. Because when I'm taking the convolution operation, what happens that suppose the convolution, the filter is applied here, then it is shifted, it is applied, say it is applied here, then it is applied here. So this pixel is having more contribution to feature learning than a corner pixel. This pixel, or even H pixel. So first of all, when you are taking the input as 256 and you are applying a 5 cross 5 filter, you saw that the output volume was coming out to be what? 252 cross 252. So from 256 cross 256, it goes to transform to 252 cross 252. And suppose you have a very deep neural network, the size will be gradually diminishing, right? And in order to, to overcome this problem or to control the problem of dimension reduction, what people have proposed is apply zero padding. So the image is there, image is of course here, which is shown here, but now I pad on each side, on each edge of the image, I'm padding it with 0. So corner as this zero padding has two advantages. One is that dimension reduction is controlled, and the other is that corner pixels have better contribution. Okay, the corner pixels will be having better contribution. All right, so output dimension in case with zero padding, let us see what happens. Now, because suppose you have a padding of 1 on both the sides, so it is twice padded on left and right. And therefore, you can see that we have chosen here padding 2p, that is the size of the image which was n becomes n plus 2p. So it is n plus 2p minus f divided by the stride. It is the greatest integer contained in that plus 1. That is all, right? So to avoid size reduction and to have better contribution of corner and edge pixels, we make use of something called padding. This is known as zero padding because we have added here zero values. So suppose the image size is n cross n, pooling width is p, stride is s, then this is the formula for the output dimension. So suppose an image is of size 64 cross 64 cross 3, there are 16 filters in a convolution layer, each of the size 5 cross 5, which is applied with a stride of 1. What will be the dimension of the output volume? What will be the dimension of the output volume? Now you can, formula is before you, so you can quickly calculate it, right? And this is very easy to calculate, find out formula. It's not a difficult formula, right? Simple mathematical expression. Now, if the padding is p is equal to 1, the output volume will change, right? If I put here padding p is equal to 1, the output volume will change. So what is the output volume initially? It is 64 minus 5, that is 59, right? Stride was 1, so 59 plus 1, so it was 60 cross 60. And since there are 16 filters, so it would be 60 cross 60 cross 16, right? That was the output. If suppose you have added a pad of 1 on both the sides, then this becomes 2. So you will be having 64 minus 5 plus 2. And then because the stride is 1 plus 1, this plus 1 is added. So you can see that in this case, you have 59 plus 3, that is 62 cross 62 cross 16. But what if you wish to have the same output? Suppose you wish to have the same output. By using this formula, you can determine, suppose you want the same output, right? Let me just erase this part. Suppose you want the input dimension and the output dimension in the spatial dimension should be the same. So what we can do is that we can write n minus f plus 2p divided by s plus 1 should be the same as n. And so in this way, you can determine the value of value of p. F is the filter, n is the size of the dimension, p is the padding. So what padding should I apply so that the output and the input image dimension remain the same? Now, one more question I am throwing before you. What will be the total number of parameters in this conv layer? How many parameters will be trained? What will be the number of trainable parameters in this conv layer? Can you tell? See, what are we learning? We are learning filters, right? So you have 5 cross 5 dimension filter, and there are 16 filters. So 25 into 16. There are 16 filters. Someone wrote here the answer. Abhishek Dobal writes 16 cross 5 cross 5 cross 3. No, I beg to differ from you. Because we have chosen 3 copies of the filter. So the same W values will be there, right? So it is 25 cross 16, right? But each filter uses its own bias and there are 16 filters. So it is 25 cross 16, right? Like 400 plus 60. Fine. So that is how the number of parameters are chosen. Now I am ready to take your questions because so many questions were being posed and I don't know if, will you please repeat your questions? If I don't answer your question, please repeat. Patterns are detected at same time or one by one. Vishwajit, I think I have answered your question. Patterns are simultaneously detected, different patterns by different filters, right? And then it's difficult to trace back. That's the reason I request you to please, whenever there is a question time, if you ask during that time, I mean, the probability that I don't miss your questions will be less. Value of filter, whether the value of filter is taken by trained model in a program. Now, values of filters are randomly chosen and then they are trained. You want me to repeat something? I hope you have understood. I don't think any questions are there. What is, I don't understand the use of activation map. What is a why use, why wasn't the RGB value of 3 not considered for calculating the final? I explained you, Nabil. Because those 3 values are added. They're added to give you one output, right? And convolution and convolution and add all the values to make it one feature map, right? And then how do you find the position of a CNN in an overall neural network means which layer and what location should have which CNN filter? I don't understand the question, but I think you are asking how many remember convolutional neural and will have several filters. Those several filters will give rise to those number of activation maps, like the same, whatever is the number of filters, those numbers of activation maps are generated. What is the purpose of activation maps? These activation maps are actually extracting features of activation maps have that role. of detecting to
Some connection problem, ma'am. There is some connection problem. The voice was breaking. Can you repeat it?
I'm sorry.
Your
Pardon?
voice was breaking actually. I think it's some connection problem. Your voice was breaking, so
Your voice is also, I don't know. So I just stop my video. Let me check. Dear friend, can you listen to me? Not audible. So many people are saying not audible. Am I able to not audible?
now it's okay, ma'am. Now it's okay.
Am I audible? No. So many people are saying not clear. Please feel okay. Now it is audible. Voice is breaking and so many people really network voice so what to do? I should use my own network. Voice is still clear, not clear. My voice.
Now it is clear, ma'am. Now it is clear. But for some time when you were explaining activation, ma'am, it was breaking actually. Now it is okay.
I'm so sorry for the inconvenience caused you. I hope that part of the convolutional is clear. What happens that whatever is the input volume, suppose you have 3 channels in an input volume. Suppose there are 3 channels in an input volume. 3 channels, right? So what we do is, let me tell you again, that suppose the image is 32 cross 32 cross 3, right? Now it has got 3 channels, RGB and RG and B. Now I considering R channel as one grayscale image, for example, you will be applying convolution operation on this R channel. After application of convolution operation, you will be getting an output. Suppose obtained, right? So I will be getting, suppose it is 4 cross 4 output, right? I will be getting this 4 cross 4 output. Similarly, on G channel, I will be doing, I will be using convolution, and I will be getting another 4 cross 4 output, right? And similarly on B channel, what I will do, and similarly on B channel, what I will do, I will be component wise adding these values. So this value plus this value plus the first value here. So the ijth value of R channel convolution output, G channel convolution output, and B channel convolution output, they will be all added to give you one single output, that is the feature map for what? Feature map for one filter, this filter that I am applying. And if there are 16 filters, then there'll be 16 this. Voice is again breaking, my dear friends. No, thank you. No, thank you so very much. Thank you so very much. So now let us look at, say, I told you convolution operation. I told you that we use a pattern detector, and that slides over the entire image. And then initially that is randomly chosen, and then slowly it is updated by looking at the errors made by the convolution operation and the convolutional layers, and those errors are back propagated and W values are updated. That means your filters are updated. Let us look at the fully connected layer. If suppose you were performing the same operation using fully connected layer. So suppose the input image is of size 32 cross 32. We will first flatten it like Purnima did yesterday, convert it to 1D vector, then dimension of the input vector will become 3072. Suppose there are 10 units in the first hidden layer of FC network, then each unit looks at the full input vector. That means it is receiving all the inputs, 3072 different inputs it is receiving. So if I have a 32 cross 32 image, I will be flagged vector of 3072. I will inputting this image in a single dimension vector, sorry, 1D vector, 1D array to a 10 neurons, right? These 10 units are there. And then I will be getting W transpose X plus B, on which I will be applying an activation function. So the trainable parameters will be what? 3072, the input dimension, multiplied by 10. So this will be the size of the weight matrix that Purnima was also telling you, and Dr. Santosh Viparthi also discussed in the first class. So weights are 30720 plus bias, number of bias parameters are equal to the number of neurons. So the total number of parameters which are trainable are 30730, as opposed to if you have only 10 neurons or 10 filters. Suppose you have only 10 filters, each of size say 3 cross 3, then you will have 90 parameters plus 10 parameters for those 10 filters. So in the case of convolution layer, the input image is 32 cross 32. There are 10 filters, each of size 3 cross 3. And the total trainable parameters will be simply 90 plus 10, including the bias parameter 100. That's all. So you can see that the number of parameters are drastically reduced, right? And therefore, the memory footprint of the neural network will be reduced. The entire computation will be reduced with respect to the image data that we have considered. That is the reason convolutional neural networks have an added advantage over the fully connected neural network for considering and processing image data. But that is not the only advantage. That parameter sharing helps reduce a number of trainable parameters. That is not the only advantage. We shall see some more advantages later. Now, this is how you can see the picture that I've taken from the Professor Ming Lee's lecture slide, that if you have an image, you use convolution operation, you get outputs of this type. And these are basically activation maps that you get. And in case of a fully connected layer, the 6 cross 6 image will be flattened to make a 36 dimensional vector. And then this is sent to the fully connected neural network. That is how it happens. All right. Now, so suppose you have filter 1. Now, I seek your attention, please. In this filter 1, we have, say, this 3, which is output, is obtained by applying filter 1 on this image block. On this image block, which is highlighted by red boundary, right? Now, this 3, so all 9 parameters which are used to compute this 3, the same parameters will also be used to compute -1 and -3 and then -1, right? So in those 9 parameters. So you can see that this 3 is computed by, say, these, I've If we use here different colors, these 9 different parameters for 9 colors. Now, if you see, you have very few parameters, right? And so fewer parameters is one advantage. But if you see that you have a sparse connection, one is that convolutional neural network has a sparse connection. Instead of having a fully connected connection, it is having a sparse connection. Secondly, that parameters are shared. The same shared weights are used. So you have even fewer parameters. You're not using another set of parameters for a different place. And you are using the same 9 parameters throughout. So what I intend to say that fewer parameters, why? Because you have a very sparse connection at a time. And at the same time, because the same connection parameters are used throughout the network, throughout the image, so you have even fewer parameters. Well, a CNN architecture, a general CNN architecture somewhat looks like this. Suppose you have a problem of binary classification of images into cats and dogs, and can be other multi-class classification as well. So generally what we do, we apply convolution layer, then pooling layer, then convolution layer, then pooling layer, sometimes some more batch normalization layer, some other layers are also added, but this is a generic architecture of a CNN. So what is this doing, my dear friends? This is doing feature extraction. Yesterday and day before yesterday, you saw some exams. You saw that neural networks, what is the difference between deep neural networks and neural networks? The deep neural networks, the first few layers are feature extractors. They do feature extraction, right? So this is doing feature extraction or pattern recognition. And then after that, the image is flattened, that is made to become a 1D array. And then this is sent to a fully connected network, feed-forward network. What for? What is the purpose? For the class of tasks that can be a classification task or that can be a regression task, right? So let me check what are the questions, like how to decide filter matrix element. We are choosing randomly, right? We are choosing randomly. Again, I was not audible, my dear friends. I don't know what's happening today.
I mean, in between sometimes it happens, but now it is clear.
I'm so sorry. Some people are saying, so CNN architecture, I am repeating again. You have a convolution layer, my dear friends, right? You have a convolution layer, right? And then you have a pooling layer. I have not yet explained what's pooling, but just for the time being, just imagine that pooling layer is there. Now, so you have a convolution layer and a pooling layer, a convolution layer and pooling layer. There can be other layers, like I told you, batch normalization layer. So this can repeat many times. The more repetitions are there, the network is deeper. It is deep convolutional neural network. Now, what happens that this part works as the feature extractor in the image understanding, right? It is working as feature extractor. Once these features are extracted, what I do, whatever is the volume, suppose after the first convolution neural network, the output volume turns out to be Suppose 32 cross 32, 32 cross 32 cross 16. Suppose this is the output volume of this, all right? Right? And then after the second convolution, suppose it becomes 28 cross 28 cross 32, right? And this 28 cross 28 cross 32 volume is flattened to become one-dimensional array, right? One-dimensional array. And then that is sent to the feed-forward network. What for? For the task that you are, for the problem that for which you are building a neural network model. That task could be a classification problem. The task could be a regression problem. So, there are several questions. I will be answering your questions one by one. Please don't worry. So feature extractor means, is it eye, ear or cat identification? Feature is much more general than this. Here in this case, in human understandable form, features are like eyes, ear. Yes, you are right. But as I told you that convolutional neural networks combine the low-level features, mid-level features to give features of higher abstraction level to understand the patterns, which could be eye, ear, nose, something like this. Now, yes, backpropagation happens along the entire network, including the fully connected layer and the convolutional layers, right? In 28 cross 28 cross 32, is the last value increased by the number of filters? Yes, the number of filters. The last value is increased by the number of filters. All right. For 1D inputs, they are converted to 2D inputs, and then features are extracted. So let us see flattening, how it is done, how the flattening is done. So suppose there are two filters, two feature maps or two activation maps. So first I will be applying flattening on the first feature map or first activation map, and then I will be applying flattening on the second activation map. So if there are 32 activation maps, I will be first flatten the first activation map, the second activation map, and the third activation map, and so on and so forth, right? Then that flattened vector is sent to fully connected network. Okay. Now, so I hope you have understood what does how a CNN structure looks like. A generic CNN architecture consists of several convolutional layers, and then after that a flattening layer is used. After the flattening layer, some fully connected hidden layers are used with an output layer that is also a fully connected softmax layer, right? It can be a softmax layer as well. So the CNN architecture also uses fully connected network at the end. That is the generic structure, but not all CNN architectures which are used for different applications use fully connected network at the end. This is one of the model that is most celebrated model, where at the end you use a fully connected network for a specific class of problems. Let us understand what is fully connected, what is a pooling layer. Now, when the image is large, you need to compress the image for managing the input and output volumes, so that the output volume becomes more manageable, right? So pooling layers make the representations smaller and output volumes become more manageable, right? So pooling is a kind of subsampling. It operates over each activation map independently, remember. So suppose you have 32 activation maps. On each activation map, it will be applying a subsampling operation to downsample the input. Frequently used pooling types are like max pooling, average pooling, and global average pooling. So what could be the advantages? Definitely it subsampling. It does not, first of all, lose image information. Secondly, this reduces the size of the output volume, and therefore memory requirement is less. So if suppose this is an this is an image which has this information that a food bowl on a wooden top, it is an image caption. The image caption or the image information will not change. It will remain the same. But remember that fewer parameters are needed to extract features for pattern recognition in this case, right? All right, so, oh, I'm sorry, something wrong. Yeah. So what is happening in case of max pooling? In case of max pooling, suppose you choose a filter for pooling of size 2 cross 2. Here it is 2 cross 2. I take this filter of size 2 cross 2 and I take the maximum value here and a maximum value here, and similarly maximum value here. So what I do is I downsample. I'm sorry, I did something wrong. I hope you understand that this is the maximum value that will be chosen, then 5, then 0, and then 4. So the output will be 7054. This will be the output from this 4 cross 4 input. Similarly here, the output will be, say 3 is the maximum, 1 is maximum, 2 is maximum, and 4 is maximum, right? So you will be getting those maximum values only. So the output will become a 2 cross 2 of size 2 cross 2. In average filtering, on the other hand, we take all the values, but we take the average of those values. Like in this case, it was 3 plus 2, that is 5 plus 7 plus 1, 13 out of 4. 13 by 4 average value, which is equivalent to 3. Similarly here, 5 by 4, which is 1, 9 by 4, which is 2, 4 by 4, that is 1. So the output will be what? 3, 2, 1, 1. That will be average pooling. Similarly on the right hand side, right? So you will be getting 0, 0, 0, 1, right? And then there is something called global average pooling, which is very much used in recently because it drastically reduces the the dimension and also accelerates to some extent training process. So here what we do, for each filter, you get a activation map. Suppose this 4 cross 4 activation map I'm getting, I will take the average of the entire spatial domain, all the data. And then similarly here, I'll be taking the average. So suppose you have 16 filters. So output will be a 1 cross 16 filter. That 1 cross 16 output. If you have 16 filters, because each filter will give rise to one activation map, and you take the average value of that activation map to take out to give you just one value or a single value. That is what I'm explaining, that I am taking the average of like 3 plus 2 minus 3 minus 1 plus 1 plus 7. I think I have explained this. Take the sum of this, divide by 16. You get 13. Similarly, take the sum of them all, divide by 16, you take 5. So that is the global average pooling, right? So then the output will be what? 13, 5. That will be the output. Okay. Is that clear to you all? Somebody is asking, what is the regression and classification problem? See, classification problem, suppose your data samples that you have yesterday in the theory and also in the lab experiments, you started like doing some classification problem, right? What is classification? Your data is, say, there are several problems which are classification. For example, you are asked to give your comments, give your like a review of a movie in a score of 1 to 5. How do you give the score? Instead of writing the general comments like movie was good, the direction, acting, everything was good and bad, whatever, you will be simply putting 4 out of 5. Or by if you are not happy, you will say 1 out of 5. So what is this? There are 5 classes in which you have classified all movies. A movie can be excellent, very good, good, average, and poor. So this is a classification, right? Similarly, regression. Suppose you have the average temperature you want to calculate for tomorrow. How will you calculate average temperature tomorrow? You will look at the past August 26 temperatures of past several years and the past week as well. And then you will be estimating the temperature, average temperature tomorrow. The value of the average temperature can lie between, in cities like Jabalpur, can lie between say some 25 to 35, depending on whether it is rainy season or it is sunny day, right? So it will all be a regression problem, okay? Now, so next question is, so how we have calculated the average? Oh my God. How can I explain to you how to calculate the average? How do you calculate the average of 5 plus 7? What is the average of 5 plus 7? It's a very simple problem, right? My dear friends, so you have to take into account this. I think I have not understood you correctly. I beg your pardon if I have not understood you correctly. So now CNN advantage in dealing with high dimensional data. First of all, number of connections are reduced. We have very sparse connection as compared to the fully connected network. Well, Mr. Dr. Somshekharji, we will be providing you link, and to everybody who is asking this question, we have been provided link. We are providing link on Canvas platform. Please go to the announcements in the Canvas platform. And Dr. Santosh Viparthi must have been facing some issues. Otherwise, he would have shared the link. So please wait for a couple of hours. I think he will be sharing the data, right? So number of connections are reduced, number one. The second thing is parameter sharing, right? Third, which is important, is pooling layers compress the output volume, right? So what happens, the input dimension was suppose the input dimension is say 512 cross 512. The memory footprint of the entire model will be large. Memory footprint of your data size will also be large. So in order to deal with this, pooling layers are introduced. How to create algorithms based on this? Now I will take your questions in a couple of minutes if you don't mind. 13 and 5 summation will. So Parul is asking, somebody is asking, 13 and 5 are not divided by 16. So my dear friend, you take integer approximation. Okay, fine. So is feature selection also implemented in CNN? CNNs are feature selectors. CNN, the layers of CNN are basically feature extractors, right? And they then select after extracting. Some people have used special feature selectors also, special algorithms for feature selection after the CNN. But I I I would say that in general, this is not the practice. Why flattening pooling layer? Why all these, madam? So Rajesh Kumar is asking why flattening layer? Because this is, if you remember, yesterday in the theory and lab class, it was told to you that in the end, suppose it is a classification problem. So the output you would like to have, say, in 5 classes, 3 classes. And so for giving an output, for the probability that an element, an input belongs to a specific class, from a probability of 5 different classes, you will be getting 5 probability values. Probability that this is a dog will be high, perhaps if the image input is containing a dog. Probability that it is containing cat will be relatively low. Probability that it is containing a car will be still low, and so on and so forth. So in out of 5 classes, if you remember, we use one hot encoding of the output probabilities, and we say that okay, this image is belonging to dog class. So if it is belonging to dog class, its dog class will contain vector value 1, rest of the values will be 0. And that is the reason we consider at the end fully connected layer. I hope I have explained to you. Is that clear to you? Manas, Rakshit, is there any rule to choose number of convolution layers? Well, that we also told you before that there's no hard and fast rule for this. People are practicing with doing with trial and error, but it is always good to choose, if you have a very large data set, to choose large number of convolution layers and large number of filters also if the data set is having variety. Okay, now let me go ahead. So then they have one thing very interesting, that is equivariant representation. You'll ask me, what is equivariant representation? Well, equivariant representation, like equivariant, right? So suppose I say that something is invariant, it doesn't change, right? It doesn't change even after some action or some operation, like a convolution operation. Even after convolution operation, if something doesn't change, we call it invariant, right? You must have heard of various transformations that are invariant under scaling, invariant under rotation. So these rotation is a kind of operation, scaling is a kind of operation, and we find out many transformations which are invariant under certain actions, right? Now, by equivariant, we means they vary with equal proportion, right? So suppose you take the maximum, for example, you take the maximum of a maximum value of the pixels of an image. Now, even if you downsize the, like if I if suppose the image size was scaled down to from 512 to 512 cross 512 to 256 cross 256, what we have not changed is the maximum value, we have only changed the image dimension, right? So what I intend to tell you here is that there are certain things which are which vary with proportion. That is, the location of the maximum value will vary with proportion. If the image initial maximum was at the midpoint of the image, the final maximum will also be at the midpoint of the image if the image is scaled down, right? That is, like, you, in the very crude form, you can call it, say, in some sense, equivariant. Now, by saying that they learn equivariant representation here in the context of CNN, I mean to say that small rotations, perturbations does not, this learning process is robust to small deviations or small rotations, small translations. It can detect the same pattern. Like, for example, to say in crude terms, if if it is an eye detector, then if there are small changes in eyes, it will be able to detect eye with small changes. So that is what is equivariant representation. Ability to work with inputs of variable size. You make a convolutional neural network, whatever is the input size, it can be, tomorrow you can take 512 cross 512, today you can take 256 cross 256. You must be thinking, what is different here? If you remember, in the fully connected network, the first layer, the very first layer, weight matrix was W, like we had W transpose X plus B. What was the dimension of the very first layer weight matrix? It depended on the on the dimension of X. It depended on the dimension of X. So it was number of elements in the first hidden layer multiplied by the dimension of, sorry, cross dimension of X, not multiplied by, H cross dimension X, right? That was the weight matrix. Here, CNNs are taking filters whose weight values do not depend on the size of the input, right? So it's having the ability to work with inputs of variable size. If you have trained a network for input images of size 256 cross 256 cross 3, and if you want to detect a pattern in, say, 302 cross 302 cross 3 image, as I told you that it learns an equivariant representation, it may give you a correct output for that image dimension as well, right? So the number of trainable parameters depend on how many filters you choose for training. And that is, like, these are some advantages of neural network. Now, before going to the history, if you have any doubts, please feel free in asking me. Can you give a small numerical example for understanding CNN like Santosh sir? Anima Nayak is asking me. Anima, I gave you some example like how CNN operations are done, right? And perhaps that is what best we can do to tell you, like, how this is multiply. Should I multiply them again? I mean, those 3 cross 3 filters. I think I have given an example. If you have not understood the example, please go through the slides one again. Those are examples. So I'm reading the questions because these questions are privately asked. And so, is there any method there pre-processing can be done in deep learning automatically, whether it can be influenced with feature extraction it will go more mileage to DL. So you mean to say that we first feature extract and then send to DL? Shallow neural networks, shallow convolutional neural networks, there are some authors who have done this, but I don't see any advantages or any breakthrough in this kind of pre-processing or feature extraction. Pre-processing is anyway done by in any CNN model. During backpropagation, filter values are updated only. Yes, filter and biases are updated. How non-trainable parameters means unused parameters? So Sesha Venkata Sriram, non-trainable parameters are those parameters which are used when you use the concept of transfer learning. What is meant by transfer learning? We train the network on a different data set and then use that trained network. That means it has learned the features of that data set. Use that trained network to do for a different kind of task, right? So here the task can be, suppose you have trained it on a general natural scenes and now you would like to do it for plant disease detection. Then what we do, suppose the neural network has 5 layers. Out of those 5 layers, 3 layers network weights we initialize as that of the trained model, right? Previously trained model or pre-trained model. The next 2 or the last 2 layers that we would like to do is to randomly select the weights of the last 2 layers. So let me take an example. You have, suppose this is a trained model, right? And here in this trained model, what I do in this trained model, I know the weights are learned. So I note the weights of these 3 layers, I freeze them. I randomly select, initialize the weights for these 5 neurons for a new type of problem. That problem I told you can be a plant disease detection problem. This network was earlier trained on a general data set. Now, so what I will do, I will initialize the values. These values I will initialize. And this, because I have frozen these values, these are non-trainable parameters. Is that clear to you? These are non-trainable parameters. How many filters can we apply? Somebody is asking. So I have already told that number of filters that you choose should be a sizable number so that you don't miss out any features. So Sheetal Patel, ma'am, I want to implement my own feature extraction algorithm for elders fall I don't know, detection data set. So you can use, definitely you can do that, no problem with that. You can use, or if you have some specific question, we can have a separate discussion. Okay, so now I come to the history. The very first that I would like to tell you is the attempt made by Frank Rosenblatt in 1957 perceptron model. When he introduced, he used a computing machine which was connected to a camera that used 20x20 cadmium sulfide photocells to produce a 400 pixel image. It was able to recognize alphabets. So this was one of the major breakthroughs. The next, in the context of convolutional neural network, was introduced by Leaken. Leaken is a legend in this field. The first CNN model was introduced by him in 1989. You can see here he used 6 feature maps. He used 6 feature maps, and then he used 6 feature maps again, then 16. and then he used a subsampling, that is a pooling layer. Then he used a fully connected layer. Like this fully connected layers were used here, these fully connected layers. And so this was introduced in this particular model was introduced in 1998. It made a history. It was shown to perform very well on this kind of image input. The next major breakthrough was in 2012 when LXNet was introduced by Krzyzewski, Sutskever, and Hinton in 2012. Hinton, as I told you, is another legend working in this area, and he has produced many legends. And in around 50 years of his research on neural networks, he has made a significant contribution in the development of the theory and applications of neural network. Now, with this, the concept of deep learning was evolved. The deep learning made sensation with this 2012 LXNet architecture. So what is this LXNet architecture? It has one convolutional layer and then a max pooling layer, a normalization layer. As I told you, normalization is done to control the drift of the output from the mean 0 and the specific standard deviation, say 1. Then it used a second convolution layer, max pool, and the third convolution layer, fourth convolution, fifth. So it used 5 convolution layers, as you can see here: first, second, third, fourth, and fifth. And after that, it used max pooling layer and then 3 fully connected layers, as you can see. Now, something that you can see here is that 2 parallelly running networks are here. Why? The reason was that even in 2012, this network was so heavy that it was difficult to train this network. The computational cost, the memory footprint was very high. In spite of this, it made a history in the ImageNet large-scale visual recognition challenge. In 2012, this was the first CNN-based winner of this large-scale visual recognition challenge, in which we have 1,000 object classes and around 1.4 million images, right? It used only 8 layers, and then 8 layers, and then 19 layers in 2014 with VGG, with GoogleNet, 22 layers, and then suddenly ResNet, I told you, with 152 layers, made a mark, another history in this, when average human perception was beaten by a machine. Remember that there are some difficult tasks like computer vision, image recognition challenge, and natural language processing, translation kind, chatbots. These are difficult tasks, and this was for the first time that in terms of, in the context of vision, human intelligence was beaten by a network. So then, since then, we have so many architectures like LXNet, I told you, VGG, 16 to 19 layers. We have GoogleNet, 22 layers. These are beautiful architectures. When you use them, when you learn about them, you will be fascinated by the kind of models they are. They're extremely efficient models, and each has its own unique feature. LXNet, as I told you, was the first of its kind. VGG is one of the best feature extractor or feature descriptor we have. GoogleNet, on the other hand, captures features of different abstraction level at the same time. So it is the uniqueness of this. ResNet is one of the first neural network, convolutional neural network, that had more than 100 layers, right? Like layers in the multiples of 100. And it was introduced by Kamin He, and This network used the concept of skip connection and got rid of the famous vanishing gradient problem in fact infamous vanishing gradient problem in training the deep neural network. So many new networks have been introduced since then. Architectures for specific applications have also been introduced. So this is VGG. It's a very simple model. It has only 3x3. It is only uses a 3x3 filters, right? 3x3 filters it uses. Now you can see it is, you have, these are max pooling layers. These are max pooling layers. So it downsamples the image dimension. And these are fully connected networks. So it's a 16 layer network. And you can see here, this is a conv layer, conv layer, conv layer. This is a conv layer, conv layer, conv layer. And so you have 3, 3, 6, 3, 9. So you can see that there are 16 layers, including the fully connected layer. What is a softmax layer? Softmax layer is just to classify the image input. Then came, so this was one of the best, it is, even now it is considered one of the best feature descriptor or feature extractor of the images, of image data set. And in spite of the fact that this is a very heavy model, people are using this for their different kind of applications. A GoogleNet, on the other hand, is a balanced model with a balanced model size and computational cost. It uses different size of filters altogether. I mean, it uses, as I told you, we used, say, 16 filters, each of size 3x3. It gives a different concept. It uses a different concept. It uses filters of varying size at the same convolution layer. So you have feature abstractions or simultaneously of different level. It then goes deeper to enrich the feature abstraction level, right? So let us consider this model. Inception module with dimension reduction. I can see many questions floating in. Please wait for a while. I'll definitely try to answer your questions. All right, so suppose you have a previous layer. Then what they do is that they use, as you can see, 3x3 convolution, 5x5, and they use 3x3 max pooling, then 1x1 convolution, and then they concatenate all the activation maps obtained after applying these convolution maps. So this is known as an inception module with dimension reduction. All right, so it has computational efficiency. Dimension reduction is achieved with 1x1 convolution. I will tell you how. And pooling in depth is done instead of max or average pooling in height and width. What is pooling in depth? So suppose you have, like, these are filters, right? So at this position XY, whatever is the value, XY position, I choose the same XY position and I do the maximum pooling. I take the maximum of these XY position obtained across all the feature maps or activation maps. So either you use max pooling or you choose average pooling. That is what is done in this case of inception module. Now you must be thinking how computational efficiency is obtained. Let us consider this 28 cross 28 cross 128 input volume coming from a previous convolution layer. And suppose I have 256 layers and I want to apply padding so that image dimension does not change. So I have applied padding so that image dimension doesn't change while doing the convolution operation, right? So the idea is from this input, I want to get this output, right? How many computations will be there? I seek your attention, please. The number of multiplication here will be 642 million approximately. Can you believe? With a 5 cross 5 convolution, applying same padding. By same padding, I mean the output and input dimensions should be the same. So let us take this feature map. Let us take this activation map or feature map. One position of this feature map is obtained how? This one position is obtained by taking a 5 cross 5 block here, right? A 5 cross 5 block here, and there are 128 such channels. So 5 cross 5 cross 128. So one position here is obtained by 5 cross 5 cross 128 multiplications. And then in the output, I have 28 cross 28 cross 256 outputs, which are here. So it is this total, the total number is this, which is around 642 million. Okay. Now, if I use a 1 cross 1 convolution, what I do is that I reduce significantly the number of filters here and I apply a 1 cross 1 convolution, right? So since I apply a 1 cross 1 convolution, so a one position here will be obtained by taking a 1 cross 1 convolution here. And since there are 128 such values, so I will be having 128 multiplications. And since there are 28 cross 28 cross 32 outputs, to get this output, there are 28 cross 28 cross 32. So that will be 128 multiplied by 28 cross 32. Then from here to here, apply the same thing. You have 5 cross 5 convolution, and each entry here will amount to 5 cross 5 cross 32. So it will be 5 cross 5 cross 32. And since there are 28 cross 28 cross 256 entries, so these many. So there is a drastic reduction in the number of multiplication required from 642 million to 163 millions. A full inception module looks like this. So I start with inception. This is the inception module, convolution or fully connected softmax. So you can see that these are all convolution maps, convolutional layers. This is a pooling layer. It keeps on growing like this. This was the first version, and then GoogleNet 5th version, 7th version, the various versions have been introduced. And I must tell you that this Linnet is especially to give credit to the fellow Leakin, who introduced the concept of convolutional neural network. If you see the computational cost comparison with VGG, in spite of the fact that Inception 7 is much more heavy compared to the previous Inception module in terms of billions of operations per second, it is, you can see the computational efficiency of Inception module. Well, many of you were asking about the book. Ian Goodfellow, I consider to be the Bible of this deep learning. Lecture slides by Ming Li, Fei Fei Li. These are two very beautiful lecture slides. Andrew Ng Coursera course, from where I learned initially long back, not very long back, 2016, 5 years back. Benchima, Syzygy, these are some important references that you can use. Thanks. And questions. Question answer session. I stop sharing now. So some people were asking that can you give more, can you give some examples? Perhaps I've given example, and if you have not understood, we will give you some assignment to deal with the, to understand, to do it yourself, right? So take home assignment. So what will happen that you will, when you do it yourself, you will understand it better. Kalpana Devi is asking, what are UNet and VNet? UNet and VNet are a special kind of encoder-decoder based convolutional neural networks that we will cover on when I talk about autoencoder day after tomorrow, my dear friends. So I will take up some questions which are written here in the chat box. Can we define the filter values depending on our classification target? Well, Navjyoti Das, in fact, filter values are defined in case of traditional image processing tasks. Like you have Sobel filters, you have Canny edge detectors, you have predefined filter values because they have those legendary figures have computed those filter values to ease our task of say image enhancement or edge smoothing or something, whatever you want, right? But here in case of CNN, these filters are learned. So you have to randomly select the filter values. Automated detection of tuberculosis from chest X-ray images using deep learning. Can you give me the whole model for block diagram idea for doing automated detection? LXNet, GoogleNet, VGG, ResNet, these are all available on GitHub. So please just Google, you will get all these models. I suggest you not to use LXNet. It is very huge model. And we have now better efficient, I mean, more efficient models which are available. All right. And then the question is also some of the references may reference area step by step. I need to start, learn and implement this as my research. Thank you, Rajesh. I think I have given you some references. And if you want to learn, do a full course. I mean, without doing a full course, I think it is always better to do a complete course. And then you will learn very well. That is what is my personal experience and suggestion, right? And then when we will receive video link of yesterday, Dr. Santosh, I think you can better answer because they don't, we don't, I mean, Dr. Santosh has the access to that. How is layering structure of any network decided? This is asked by Mehak Jindal. Layering structure of any network is decided based on the variety, variety in the data, and also on the size of the data. So as I told you, if the data set is small, but it is having variety, then you can use any pre-trained model and can use transfer learning, as I explained, to have your task done, right? So generally it is decided by trial and error. And thank you, Seemaji. How is the layering and then when we will receive, okay, that's all I think so. I think that's all. Medical image segmentation with CNN nets are good. There is no net which is good or bad for a specific problem. You will have to do it yourself. We are trying like thousands, hundreds we have tried, and we can see that like my students, Dr. Preeti Khanna's students, and all our students have been trying for different applications, different kind of network. They're designing new networks like Purnima is doing, Shubhangi is doing. So you have to design your own network for a specific class of problem. but definitely we will tell you. Is padding always good to use? Well, if I mean, most of the networks use padding, but if the image size is too large and there is no information that is given at the corners, like sometimes, engineering drawing, one of our students, Nishant Khare, is doing some problems related to engineering drawing. Those engineering drawings are only at the middle of the picture. The corner pixels are of, so there we don't require padding. Okay. So with this, I sincerely thank all the participants for your active role. I hope you will maintain your active role in your lab class also. And don't worry if you don't understand it now, because what happens that in the first go, like what I covered in 2 hours is generally covered in 6 to 8 hours, right? So in the first go, it is not always possible to get to understand everything. But with time, when you keep on experimenting and practicing, I'm sure that you will be able to learn it. And because you become, after you receive the certificate, you become an alumnus of EICT academies, all the 7 academies. So you can take help from us as an alumnus as well at a later date, right? Yes, it is possible to give 2 different inputs, and the model architecture is different in that case. The question is it possible to give 2 different inputs like text and image at the same time to a deep learning model? Yes, the answer is yes. Can we merge VGG19 and DenseNet to perform the task? Definitely yes, partly VGG-net has been VGG19, some layers have been merged with some other layers of other network to have a better output. I think time is over. Let's have a half an hour break. You also, if you are sitting at your institution, you can go back home. And if you're at home, have a good tea with your family members, enjoy your tea, relax, and then come back at 5:30, okay? We will have a session by Miss Monu Verma, who has completed her PhD with Dr. Santosh Viparthi, another very brilliant student. Thank you. So I take your...
Thanks for your wonderful lecture.
Thank you.
Hello?
Santoshji, they are asking for...
Yeah, yesterday's link, we'll going to share the yesterday's link. From today onwards, there will be no issue for the link. The things are...
because today we have YouTube link. So today there will be no issue. So
yeah, for
that's all.
Every day lab sessions links will be going to be shared to them, and lectures will be available in YouTube. So today, yesterday's links also I'm going to share in 5-10 minutes.
Okay, and what about, can we also do YouTube streaming of lab sessions? So that
if
I
you wish,
think this will become easy for you and for the participants as well, if it is possible.
It is possible. It is
okay.
possible.
Yeah. Then I think we should do that. Yeah. Thank you so much. Thank you so much, Dr. Viparthi, all the panelists and all the participants.
Thank you, ma'am. Thanks for your really today. We have covered all in-depth knowledge of all basic concepts. I think all the participants might be having, what are the doubts they have, they might be clear. I'm really thankful, ma'am.
Thank you. Thank you, Santosh. Thank you.